The thermometer in Eli Thornton's cabin read 42 degrees Fahrenheit in the corner farthest from the fireplace, while his neighbor James Caldwell's cabin, just 30 yards away, measured 28 degrees below freezing in the same location. Settlers crowded into Eli's small structure that January night in 1849, pressing their hands against floorboards that radiated impossible warmth, trying to understand how heat could rise from beneath their feet. Before we dive in, let us know where you're watching from, and if stories like this move you, hit that subscribe button, because tomorrow's episode is even more unbelievable than this one. The winter of 1847 hit the Montana Territory settlement with a brutality that veterans claimed was unprecedented. Temperatures dropped to 30 below zero and stayed there for 6 consecutive weeks. Game disappeared into deep cover. Creeks froze solid to their beds. Inside the dozen cabins scattered along the valley, settlers huddled close to their fireplaces and endured conditions that tested the limits of frontier resilience. William Garrett lost 3 toes on his left foot in late January. The injury happened inside his own cabin, not out on a trap line or while hauling wood. He had been sleeping in the corner farthest from the fireplace when frostbite set in during the night. By morning, his toes were white and numb. By afternoon, they were black. The settlement had no doctor. Catherine Brennan, who had nursing experience, did what she could, but the tissue was dead. She amputated using a heated knife and whiskey for anesthetic. William survived, but he would walk with a limp for the rest of his life. The incident shook the small community. Frostbite was expected outdoors. Losing body parts while sleeping inside your own shelter crossed a psychological line. At the community gathering the following Sunday, held in Samuel Hartwick's cabin, the conversation kept returning to the same uncomfortable reality. Their cabins were not warm enough. Eli Thornton sat in the back and listened. He was 34 years old, lean and weathered from 8 years in the territory. He had come west in 1839 from Pennsylvania. He had built his cabin in 1840 using standard methods: logs notched at corners, mud chinking, a stone fireplace, a single room measuring 16 feet by 20 feet. The structure kept out wind and rain. The fireplace provided heat, though that heat rose to the ceiling and escaped through gaps in the roof, while the floor remained perpetually cold. During the meeting, Eli studied William Garrett's face. The man sat near the fire, his bandaged foot elevated on a wooden crate. He looked diminished, as if the loss of 3 toes had taken more than just tissue. The expression Eli saw was resignation. This was simply how frontier life worked. You accepted hardship, you adapted, you survived, or you did not. Cold floors were a fact of winter. You slept near the fireplace, you wore heavy socks, you endured. But Eli found himself unable to accept that logic. He kept thinking about the floor. In every cabin in the settlement, the floor was the coldest surface. Heat from the fireplace rose. Basic physics. Warm air went up, cold air sank. The floor, in contact with frozen ground beneath, became a thermal drain. No amount of fireplace burning could overcome that fundamental problem. The heat went up and out. The cold came up from below. And people like William Garrett paid the price. Eli could not stop thinking about warm floors. The obsession followed him through his daily routines, checking trap lines, splitting firewood, tending to the small vegetable plot Margaret maintained behind the cabin. His mind kept circling back to a memory from 12 years earlier, before he had come west, when he was still working in the textile mills of eastern Pennsylvania. The Ashford Mill in Lancaster County had been a massive operation by 1835 standards. 3 stories of brick and timber housing, dozens of looms powered by a central water wheel. Eli had worked there for 2 years as a maintenance carpenter, responsible for repairing the wooden frames that held the machinery and fixing the floors that took constant punishment from heavy equipment. The work was monotonous and poorly paid, but it taught him how large structures were built and maintained. What Eli remembered most clearly about the Ashford Mill was not the looms or the water wheel, but the floor of the main work area. In winter, when outside temperatures dropped below freezing, most buildings became miserably cold. Workers in warehouses and shops wore multiple layers and still shivered, but the Ashford Mill floor remained remarkably warm throughout the coldest months. Eli had noticed it immediately. Standing on the worn floorboards felt different than standing on cold ground or frozen wood. There was warmth rising from below. He had asked the foreman about it one afternoon during a repair job. The foreman, a Scottish immigrant named Douglas Mackay, had explained the system with obvious pride. The mill owner had installed iron pipes beneath the main floor, connected to the boiler that powered the steam engine. Hot water from the boiler circulated through the pipes using natural convection. The pipes transferred heat to the space beneath the floorboards. The result was a warm floor that kept workers comfortable and reduced the moisture problems that plagued most mills. Mackay had shown Eli the system during a maintenance inspection. They had pried up several floorboards in the corner of the work area to access a damaged section of pipe. Eli saw iron pipes running parallel to each other, spaced about 2 feet apart, embedded in a bed of sand and gravel. The pipes were hot to the touch. The sand around them was warm. Heat radiated upward through the floorboards in steady, even waves. The foreman explained the basic principles. Water heated in the boiler expanded and became less dense. The hot water rose and flowed through pipes positioned at a slight upward angle as the water traveled through the pipes and cooled slightly. It became denser and flowed back toward the boiler through return pipes. The circulation was continuous as long as the boiler maintained temperature. No pumps were needed. Physics handled the movement. Eli had found the system fascinating at the time, but had given it little thought after leaving the mill to head west. Factory systems seemed irrelevant to frontier life. But now, sitting in his cabin and thinking about William Garrett's frozen toes, the memory returned with sudden relevance. The principle that warmed a factory floor could warm a cabin floor. Hot water circulating through underground pipes could solve the exact problem that had cost a man his toes. The community gathering in early February brought most of the settlement's families together in Samuel Hartwick's cabin. The official purpose was to discuss spring planting schedules and coordinate seed sharing, but the conversation quickly returned to the winter's harsh conditions and William Garrett's injury. Several families had experienced close calls with frostbite. Children were sleeping between parents near fireplaces. The elderly were suffering from constant cold exposure. Eli had not planned to speak. He was not a natural leader in the community. He kept to himself mostly, focused on his own land and family. But as he listened to the resigned acceptance in people's voices, the assumption that cold floors were simply an unchangeable fact of frontier existence, something shifted in his thinking. He stood up. The room quieted. Eli was not known for speaking at gatherings. Margaret looked at him with surprise. He cleared his throat and explained what he remembered from the Pennsylvania mill. Hot water pipes beneath floors, heat rising from below, warm surfaces even in the coldest weather. He proposed that the same system could be adapted for frontier cabins. The initial response was polite silence. Then Samuel Hartwick, the eldest settler in the room at 58 years old, laughed. It was not a cruel laugh, more amused than mocking, but it carried clear dismissal. Hartwick explained patiently, as if to a child, that mill owners had resources that settlers did not. Steam boilers, professional engineers, unlimited iron and labor. A frontier cabin was not a factory. The comparison was absurd. James Caldwell, who had more formal education than most settlers, began calculating costs aloud. Iron pipes were expensive even in eastern cities. Out here in the territories, they were prohibitively costly. A system like Eli described would require dozens of feet of pipe, custom fittings, and skilled installation. The investment would exceed the cost of building the entire cabin. And for what? Slightly warmer floors? The whole idea was impractical to the point of foolishness. Other voices joined in. Where would the hot water come from without a steam boiler? How would circulation work without pumps? What about leaks underground where you could not access them for repairs? What about the weight of water-filled pipes stressing floor joists? The questions came rapid fire, each one highlighting another apparent impossibility. Eli tried to explain that circulation could happen naturally through convection, that the fireplace could heat water without a steam boiler, that proper installation would prevent leaks. But his explanations sounded weak even to his own ears. He was proposing something he had seen work in a controlled factory environment and claiming it could be adapted to crude frontier conditions with minimal resources. The gap between theory and practical implementation seemed vast. Thomas Brennan, the settlement's blacksmith, was the only person who did not immediately dismiss the idea. He sat quietly through the discussion, stroking his beard, calculating. Something in his head. Finally, he spoke. Iron pipe could be fabricated. It would be expensive and time-consuming, but possible. The real question was whether Eli understood the engineering well enough to make the system actually work. Theory was one thing. Execution was entirely different. The meeting moved on to other topics. Eli sat down, feeling Margaret's hand squeeze his arm in silent support. Around him, he heard whispers and suppressed laughter. By proposing something so outlandish, he had marked himself as impractical, a dreamer disconnected from frontier realities. But as the meeting continued, Eli's mind was already working through the technical challenges, calculating dimensions and slopes, visualizing how factory principles could translate to a 16 by 20-foot cabin. 3 days after the community gathering, Eli visited Thomas Brennan's forge. The blacksmith's operation was the most sophisticated enterprise in the settlement, consisting of a stone forge, a leather bellows powered by a foot treadle, an anvil mounted on a massive oak stump, and an impressive collection of tools Thomas had accumulated over 15 years of frontier metalwork. Thomas did everything from shoeing horses to repairing broken wagon hardware to fabricating custom tools. He was skilled, expensive, and essential to the community's survival. Eli found Thomas working on a replacement hinge for Samuel Hartwick's cabin door. The blacksmith looked up as Eli approached, nodded acknowledgement, and continued hammering the cherry-red iron into shape. Eli waited. You did not interrupt a blacksmith mid-work. When Thomas finally plunged the hinge into his water trough and steam hissed into the cold air, he turned his full attention to Eli. Eli explained what he needed. Iron pipes, threaded on both ends, approximately 1 inch in interior diameter. He needed 40 feet of pipe in 8 5-foot sections, plus corner fittings to connect them at right angles. He also needed a custom water reservoir that could be integrated into a fireplace, with inlet and outlet connections for the pipe system. The fabrication would require precision. The threads had to be tight enough to prevent leaks, but not so tight that assembly became impossible. Thomas listened without interrupting. When Eli finished, the blacksmith was quiet for a long moment. Then he asked the practical questions. Did Eli have iron stock, or would Thomas need to source it? Did Eli understand that threading pipe by hand was time-intensive work that would take weeks? Did Eli realize the cost would be substantial, probably more than Eli had earned from an entire season of trapping? Eli had anticipated these questions. He had spent the past 3 days taking inventory of his resources. He had iron stock from a broken wagon he had purchased the previous year, specifically for its metal components. The wagon had broken an axle beyond repair, but its iron fittings, hinges, and reinforcement straps represented pounds of valuable material. He offered it all to Thomas as partial payment. For the labor, he proposed a different arrangement. He would work for Thomas through the spring and summer, providing carpentry and general labor in exchange for the pipe fabrication. Thomas considered the offer. The iron stock was worth something, though not as much as finished pipe. The labor arrangement was interesting. Thomas had been considering building an addition to his forge for storing coal and stock materials. Skilled carpentry would make that project feasible. The blacksmith walked slowly around his forge, thinking, calculating the time and effort required against the value of what Eli offered. Finally, Thomas spoke. He would fabricate the pipes, but on one condition. If the system failed, if Eli's underground pipes proved to be an expensive, buried mistake, Thomas wanted it known that he had warned against the project. His reputation as a craftsman depended on creating things that worked. He would not be associated with a public failure. Eli agreed immediately. If the system failed, the failure would be entirely his. They shook hands. Thomas said he would begin work the following week, once he completed his current commitments. The pipe sections would be ready by summer. The reservoir would take longer, requiring custom metalwork Thomas had never attempted before. Eli left the forge with a mixture of excitement and apprehension. He had committed his resources and his labor to an idea that most of the settlement considered foolish. There was no turning back now. Eli spent the late winter months studying the problem of water circulation. He had told the community that convection would move water through the pipes without pumps, but his actual understanding of the physics was incomplete. He knew hot water rose and cold water sank, but translating that general principle into a functioning system required more precision than he currently possessed. He started with small-scale experiments. Using tin cups salvaged from worn-out cookware, he created miniature pipe systems. He soldered short sections of tin together at various angles, filled them with water, and heated one end over the fireplace. Margaret watched these experiments with patient curiosity, moving around the dozens of tin contraptions that gradually took over their cabin's table and floor space. The first experiments failed. Water heated at one end, but did not circulate. It simply boiled away or remained stagnant. Eli realized that the angle of the pipes mattered critically. If pipes were level, hot water had no path to follow. If pipes angled too steeply, water would not flow smoothly. He needed to find the precise slope that encouraged circulation without creating air pockets or flow restrictions. Through dozens of tests, he discovered that a slope of approximately 1 inch of rise per 10 feet of horizontal distance worked best. At that angle, hot water rose naturally through the system, while cooler water returned through lower pipes. The circulation was gentle but continuous as long as heat was applied. Too much slope and water rushed through too quickly to transfer heat effectively. Too little slope and circulation stalled. He also discovered the importance of thermal mass. In one experiment, he buried a tin pipe system in a box of sand and heated one end. The sand around the pipes absorbed heat and retained it for hours after he removed the heat source. The sand acted like a battery, storing thermal energy and releasing it slowly. This observation was crucial. If he embedded his iron pipes in sand beneath the cabin floor, the sand would capture heat from the hot water and radiate it upward continuously. Eli began calculating the specifications for his actual system. His cabin measured 16 feet by 20 feet. He would run pipes in parallel lines from the fireplace end to the far wall, spaced 2 feet apart. Each pipe run would be approximately 18 feet long. He would need 8 parallel runs to cover the floor width, requiring 144 feet of pipe total, not the 40 feet he had initially told Thomas. When Eli returned to the blacksmith with revised calculations, Thomas stared at him for a long moment. The amount of iron and labor had just increased more than threefold. The cost would be enormous. Thomas asked if Eli was certain about this. Eli said he was. Thomas shook his head slowly, but agreed to the expanded fabrication. He would need Eli's labor for a full year, not just spring and summer. Spring came late in 1848. Snow lingered through April. The ground remained frozen until early May. Eli spent those waiting months preparing for the excavation, sharpening tools, organizing materials, and explaining the project to Margaret in detail. She listened carefully, asked practical questions about timeline and disruption to their household, and ultimately gave her quiet support. They would need to move out of the cabin during construction. They built a temporary shelter against the cabin's exterior wall, essentially a lean-to with a canvas roof where they would sleep and cook for the duration. In mid-May, when the ground finally thawed enough to work, Eli began digging. The plan was to excavate the entire interior floor to a depth of 18 inches. This would provide space for a sand bed beneath the pipes themselves, and additional sand above them before new floorboards were installed. The existing floor came up relatively easily. The puncheon logs that had served as floor surfaces were worn and needed replacement anyway. Beneath the floor, Eli encountered the reality of Montana soil. The top 6 inches were relatively loose earth mixed with rocks and roots. Below that, the soil became dense clay that resisted the shovel. Each shovelful required effort. The work was backbreaking. Eli's hands blistered despite calluses earned from years of frontier labor. His back ached constantly. Progress was measured in square feet per day, not square yards. The cabin's interior dimensions meant he was excavating approximately 320 square feet to a depth of 18 inches. That translated to roughly 15 cubic yards of soil that had to be removed through the cabin's single door. Eli worked alone. He had considered asking for help, but decided against it. The community already viewed this project as foolish. He would not ask them to participate in what they considered a mistake. By the end of the first week, he had cleared about 1/3 of the cabin's interior. The removed soil piled up outside, creating a mound that Margaret suggested using for an expanded garden bed. Eli worked from dawn until dusk, stopping only for meals Margaret brought to him. His daughter Rachel, age 6, sat in the doorway sometimes and watched her father dig, asking questions about why the floor needed to be so deep. The excavation revealed the cabin's foundation, or rather the lack thereof. Like most frontier structures, the cabin sat directly on the ground with only minimal stone placement at corners. Eli realized that his new floor system would actually improve the cabin's structural stability. The sand bed would distribute weight more evenly than the previous dirt base. 3 weeks into excavation, James Caldwell stopped by. He stood in the doorway, looking at the massive hole Eli had created inside what had been a functional cabin. Caldwell said nothing, just shook his head and left. That evening, Eli overheard conversation from passing neighbors. They were calling it Thornton's Folly. The name spread quickly through the settlement. Thomas Brennan delivered the first section of iron pipes in late June, 8 5-foot lengths of pipe, each threaded at both ends, weighing approximately 12 pounds per section. The pipes were beautiful in their functionality. Thomas had worked the iron with precision, creating threads that were clean and uniform. The metal was still slightly warm from the forge. Eli ran his hand along the smooth surface, feeling the quality of the craftsmanship. The 2 men carried the pipes inside the excavated cabin. Margaret had swept the dirt floor clean in preparation. Eli had already marked the layout using stakes and string, creating a grid that showed exactly where each pipe would run. The pattern was simple but specific. 8 parallel pipes running from the fireplace wall to the opposite wall, spaced exactly 24 inches apart, each positioned at a precise 1-inch rise per 10 feet of run. Thomas had also fabricated the corner fittings, L-shaped connectors that would allow Eli to create a continuous path for water flow. The design was elegant. Water would enter at the fireplace, flow through the first pipe to the far wall, turn 90 degrees through a fitting, return through the second pipe, turn again, and continue in a serpentine pattern through all 8 pipes before returning to the fireplace. Reservoir. One continuous loop covering the entire floor. The critical challenge was maintaining the proper slope throughout. Eli had built a level using a glass tube partially filled with colored water, suspended in a wooden frame. By checking this level against his pipes, he could ensure the 1-inch per 10 feet slope remained consistent. He started at the fireplace wall, where the pipes would be highest, and worked toward the far wall where they would be lowest. Each pipe had to be positioned with absolute precision. Eli dug shallow trenches in the dirt floor using a small spade, creating channels for the pipes to rest in. He placed flat stones beneath each pipe at regular intervals, creating support points that maintained the exact elevation. The work was meticulous. An error of even half an inch in slope could disrupt circulation throughout the entire system. Margaret brought their daughter to watch the installation. Rachel asked why the pipes had to be so straight, why they could not just curl around like a snake. Eli explained that water flowing through pipes needed smooth paths without sharp bends or elevation changes that could trap air. The pipes had to be precisely positioned, or the system would fail. Thomas returned the following week with the remaining pipe sections and helped Eli complete the layout. The blacksmith had initial skepticism, but found himself impressed by Eli's precision. Every pipe was positioned exactly according to plan. The slopes were consistent. The spacing was uniform. Thomas admitted that whatever else happened, the installation showed careful engineering. With all pipes positioned and connected, Eli faced the challenge of embedding them properly. The pipes could not simply rest on dirt. They needed to be surrounded by material that would conduct heat efficiently, provide structural support, and remain stable as water heated and cooled through seasonal cycles. Sand was the obvious choice, but not just any sand would work. Eli spent 2 days at the creek bed a quarter-mile from his cabin, selecting sand with specific characteristics. He rejected fine silt that would compact too densely and hold moisture. He rejected coarse gravel that would leave air gaps around the pipes. He wanted medium-grained sand that would pack firmly but maintain enough porosity for drainage and air circulation. He filled canvas bags with approximately 2,000 pounds of sand and hauled it back to the cabin over multiple trips. The sand had to be dry before installation. Wet sand would create steam pockets when the system was heated, potentially causing pressure problems or uneven heat distribution. Eli spread the sand on canvas tarps in the sun for 3 days, turning it regularly until moisture content was minimal. Margaret helped with this process, using a rake to spread the sand thin for faster drying. The installation began with a base layer. Eli poured sand around and beneath each pipe, working carefully to avoid shifting their positions. He used a wooden tamper to compact the sand gradually, creating a firm bed that would support the pipes without stressing the joints. The compaction had to be uniform. Areas of loose sand would settle over time, potentially creating low spots that would trap water and disrupt circulation. The process was tedious. Each section of pipe required sand placement from multiple angles to ensure complete coverage without air pockets. Eli developed a technique of pouring sand along one side of a pipe, tamping it, then pouring along the other side, gradually building up layers until the pipe was half buried. Then he would add sand on top, tamping between additions, until the pipe was completely embedded with 3 inches of compacted sand above it. Daniel Moss, a younger settler who had shown genuine interest in the project, stopped by to observe. Eli explained the thermal mass principle. The sand would absorb heat from the pipes and retain it for hours. Even if the fire went out overnight, the sand bed would continue radiating stored heat upward through the floor. The system was not just moving hot water through pipes, it was creating a massive heat battery beneath the entire cabin. The sand bed installation took 2 full weeks. By mid-July, the pipes were completely buried beneath a uniform layer of compacted sand. The excavated cabin interior now looked like a sandbox, level and smooth, ready for the final layer of floorboards. Eli stood in the doorway and studied his work, calculating heat flow patterns in his mind. The pipe network required a water source that could heat continuously and feed the circulation system. Standard frontier fireplaces were not designed for this purpose. They radiated heat into the room and vented smoke through a chimney. Eli needed something different, a fireplace that could also function as a boiler without requiring constant attention or creating safety hazards. Thomas Brennan had been working on the reservoir design throughout the summer. The concept was straightforward, but the execution was complex. He fabricated a rectangular iron box measuring 2 feet wide, 3 feet long, and 1 foot deep. The box would sit inside the fireplace base, integrated into the stone structure, positioned where it would receive direct heat from burning wood, but remain protected from direct flame contact that might cause the metal to fail. The reservoir had 2 threaded openings. One at the top corner would serve as the hot water outlet connecting to the first pipe in the floor system. One at the bottom corner would serve as the cold water return, connecting to the final pipe after water had circulated through the entire serpentine path. The positioning was critical. Hot water needed to exit from the highest point where heated water naturally accumulated. Cold water needed to return at the lowest point where cooled, denser water would sink. Thomas delivered the reservoir in early August. Together, he and Eli modified the existing fireplace to accommodate it. They removed several stones from the fireplace base, creating a cavity that would hold the reservoir. The iron box fit snugly into this space. They rebuilt the stonework around it, leaving the top surface of the reservoir exposed inside the fireplace, where it would receive maximum heat transfer from the fire above. The connections between reservoir and floor pipes required careful sealing. Eli used a mixture of pine tar and oakum, the same material used to seal ship hulls, wrapping it around the threaded joints before tightening the connections. Each joint was tested by filling that section with water and checking for leaks. Any seepage required disassembly, additional sealing material, and reassembly. The process took 3 days before all connections were secure. The reservoir also needed a filling port. Eli installed a threaded cap at the top that could be removed to add water. The system would require periodic refilling as small amounts of water evaporated or escaped through microscopic seepage. Eli calculated that the entire system held approximately 15 gallons when full. He would need to check water levels weekly and add water as needed. With the reservoir installed and connected, the system was mechanically complete. All that remained was filling it with water, lighting a fire, and discovering whether months of planning and labor would result in warm floors or an expensive buried failure that would confirm the community's skepticism. October 4th, 1848. The morning was cold enough that Eli could see his breath inside the cabin. Margaret and Rachel stood near the doorway, watching as Eli prepared to test the system for the first time. He had spent the previous week installing new floorboards over the sand bed, leaving small gaps between boards to allow any trapped moisture to escape during initial heating. Eli opened the reservoir filling port and began pouring water. He used creek, water that he had allowed to settle overnight, so sediment would drop out. Cloudy water could leave deposits in the pipes. He poured slowly, listening to the gurgling sounds as water filled the reservoir and began flowing into the pipes. When water started flowing back through the return pipe, he knew the system was full. He added another gallon to ensure no air pockets remained, then sealed the filling port. The fireplace was prepared with kindling and split pine. Eli had chosen pine deliberately despite its tendency to burn hot and fast. He wanted maximum heat for this first test. He lit the kindling and watched flames spread through the firebox. Within minutes, the fire was burning vigorously, flames licking around the stones that surrounded the buried reservoir. Nothing happened. Eli had not expected immediate results, but the waiting was difficult. Margaret brought coffee and sat on the temporary bench Eli had built along one wall. Rachel asked how long it would take. Eli said he did not know. The water needed to heat enough to expand and become buoyant. The circulation needed to overcome the inertia of cold, motionless water filling the pipes. Physics required time. 2 hours passed. The fire burned steadily. Eli added wood regularly, maintaining strong heat. He placed his hand on the floorboards near the fireplace. They were warm, but that could be radiant heat from the fireplace itself, not from the pipes below. He moved to the center of the cabin and touched the floor there. Slightly cool, same as it had been before lighting the fire. 4 hours after lighting the fire, Eli noticed a change. The floorboards in the center of the cabin, far from the fireplace, felt different, not warm exactly, but less cold. He pressed his palm flat against the wood and held it there. There was subtle warmth, barely detectable. Margaret came over and placed her own hand on the floor. She looked at Eli and nodded. Something was happening. By evening, approximately 6 hours after lighting the fire, the change was unmistakable. Every section of the cabin floor was detectably warm to the touch. The warmth was not intense, not the kind of heat you would feel from standing near a fireplace, but it was present throughout the entire floor surface. Heat was rising from below. Eli walked around the cabin, touching different areas. The floor near the fireplace was warmest. The far corners were cooler, but still noticeably warmer than they had been that morning. The system was working. Water was circulating through the buried pipes, transferring heat to the sand bed, and that heat was radiating upward through the floorboards exactly as he had calculated. James Caldwell appeared at Eli's door 3 days after the system began operating. Word had spread through the settlement that Thornton's heating experiment was apparently functioning, though most people remained skeptical. Caldwell had come to investigate personally. He was a practical man, educated enough to understand basic principles, but suspicious of claims that seemed too good to be true. Eli invited him inside. The October morning was cold, frost covering the ground outside. Inside the Thornton cabin, the air felt noticeably warmer than typical frontier structures at this time of year. Caldwell looked around, studying the room for tricks. He walked to the fireplace and confirmed that it was burning normally, no larger or hotter than any other fireplace. Then he walked to the far corner, the area farthest from the heat source. He knelt down and placed both hands flat on the floorboards. His expression changed. The floor was warm, not scalding, not even particularly hot, but unmistakably warmer than the air temperature. Caldwell moved to different areas of the floor, testing each section. The warmth was present everywhere, though intensity varied with distance from the fireplace. He stood up and looked at Eli with something between surprise and confusion. Caldwell asked the obvious question: how was this possible? Eli explained the circulation system, the heated water flowing through buried pipes, the sand bed acting as thermal mass. Caldwell listened, then asked more specific questions. What prevented airlocks in the pipes? How did Eli maintain consistent water levels? What happened if a pipe joint failed underground? Eli answered each question methodically, describing the slope calculations, the filling port system, the tar and oakum seals designed to last decades. Thomas Brennan arrived while Caldwell was still examining the floor. The blacksmith had fabricated the pipes, but had remained skeptical about the overall concept. He greeted Caldwell, then walked around the cabin, touching the floor in different locations. His reaction was more measured than Caldwell's, but equally genuine. The system worked. The engineering was sound. Heat was distributing evenly across the entire floor surface. Samuel Hartwick came by that afternoon, bringing 2 other settlers. With him, they had heard reports, but needed to verify personally. Hartwick was the settlement's elder, the man whose initial laughter at the community meeting had set the tone for widespread skepticism. He entered the cabin, removed his hat, and spent several minutes examining the floor without speaking. Finally, Hartwick addressed Eli directly. He acknowledged that the system functioned. The warm floor was undeniable, but he questioned the practicality. The installation had taken months. The material cost was substantial. The labor investment was enormous. Yes, the floor was warm, but was it worth the effort? Most families could not afford such a project, even if they wanted to attempt it. Eli did not argue. He simply stated that William Garrett's frostbite had happened on a floor identical to the one in Hartwick's cabin. This floor would prevent such injuries. The value calculation depended on what you thought frozen toes were worth. Hartwick had no response to that. He left without further comment. The real validation came with the first serious cold spell. November brought temperatures that dropped to 15 degrees below zero for 3 consecutive nights. This was the condition that separated functional shelter from merely adequate shelter. In standard frontier cabins, families huddled within a few feet of their fireplaces, sleeping in shifts to maintain fires through the night. Children slept between parents. The elderly suffered from constant cold exposure. Morning brought the painful process of leaving warm spots near dying fires to restart them and begin another frigid day. In the Thornton cabin, the experience was fundamentally different. Eli maintained a moderate fire through the evening, adding wood before bed, but not stoking it to maximum heat. The fire burned down overnight, reducing to coals by morning. In a standard cabin, this would mean waking to interior temperatures barely above freezing. In Eli's cabin, the floor remained warm throughout the night. The thermal mass effect Eli had calculated was proving itself. The sand bed beneath the floor had absorbed heat throughout the evening when the fire burned strongly. As the fire diminished, the sand released stored heat gradually. The floor temperature dropped slightly but remained well above ambient temperature. Even in the coldest corner of the cabin, farthest from the fireplace, the floor stayed warm enough that touching it with bare feet was comfortable. Margaret noticed the difference immediately. In their previous winters, she had worn heavy wool socks to bed and still woke with cold feet. Now she slept without socks and woke comfortable. Rachel, who had previously complained about cold floors during morning routines, now walked barefoot from her sleeping area to the table without discomfort. Catherine Brennan visited on the second day of the cold spell. She came ostensibly to borrow salt from Margaret, but really to experience the cabin's warmth firsthand. Catherine had been one of the few community members who had not openly mocked Eli's project, though she had remained quietly skeptical. She stepped inside and immediately felt the difference. The air temperature in the cabin was not dramatically warmer than outside, perhaps 35 degrees compared to 15 below. But the radiant warmth from the floor changed the experience completely. Standing on a warm surface made the air temperature feel far more comfortable. Catherine walked slowly around the cabin, her expression thoughtful. She asked Margaret specific questions. Did they use more firewood than before? Actually less, Margaret said. The system was remarkably efficient. Catherine sat on the bench and removed her boots. She placed her feet flat on the floor and closed her eyes. After a moment, she spoke quietly. This was not just warmer. This was different. This changed everything about living through winter. She stayed for an hour, mostly silent, simply experiencing what a frontier cabin could be when engineering replaced resignation. That evening, Thomas Brennan appeared with thermometers. He wanted measurements, not impressions. The blacksmith had become personally invested in the project's success since fabricating the pipes. He placed one thermometer in the Thornton cabin's far corner, one in James Caldwell's cabin's equivalent corner, and one outside. They would check readings at dawn, January 12, 1849. The morning Thomas Brennan had chosen for his official temperature measurements was bitterly cold. Overnight temperatures had reached 30 below zero. This was extreme even by Montana Territory standards, the kind of cold that killed livestock and threatened human survival. The sky was crystalline blue, cloudless, the kind of weather that combined lethal cold with deceptive beauty. Thomas collected his thermometers at dawn. He recorded the readings carefully, using a small notebook he kept for forge calculations. The outside thermometer read negative 28 degrees Fahrenheit. Caldwell's cabin, which used standard fireplace heating, showed negative 1 degree in the far corner. The fireplace had burned through the night, consuming significant wood, but heat rose to the ceiling and escaped while the floor remained frozen. In the Thornton cabin, the thermometer read 42 degrees Fahrenheit in the corner farthest from the fireplace. The fire had burned down to coals overnight. Eli had not added wood since midnight. Yet the floor remained warm enough that the air temperature 6 inches above the floorboards was 43 degrees above the outside temperature and 43 degrees above the equivalent location in Caldwell's cabin. Thomas double-checked his measurements. He moved thermometers to different locations within each cabin. The pattern held. The Thornton cabin maintained comfortable temperatures throughout. Caldwell's cabin showed dramatic temperature gradients, warm near the fireplace, frozen elsewhere. The difference was so substantial that Thomas initially suspected his thermometers were faulty. He borrowed thermometers from 2 other settlers and repeated the measurements. The results were consistent. Word spread quickly. By mid-morning, a dozen settlers had gathered at the Thornton cabin. They examined the thermometers themselves, checked Thomas's written records, and experienced the warm floor directly. The evidence was incontrovertible. Eli's underground pipe system created interior conditions that were not just slightly better, but fundamentally different from standard cabin heating. Samuel Hartwick arrived late in the morning. He had not participated in the initial crowd, but had heard the measurements discussed. He stood in the doorway, studying the scene. Settlers who had mocked the project months earlier were now sitting on Eli's floor discussing how the system could be replicated. Hartwick approached Eli directly. The elder settler's expression was difficult to read. He was not a man who admitted error easily. He looked at Eli for a long moment, then spoke simply. He had been wrong. The investment of time and materials was justified. The system worked better than anyone had anticipated. Hartwick extended his hand. Eli shook it without comment. The gathering turned into an impromptu technical discussion. How much iron pipe was needed? Could the system be scaled to larger cabins? What about cabins without stone fireplaces? Could clay or wood reservoirs substitute for iron? Eli answered questions patiently, explaining principles while acknowledging uncertainties. He had built one working system. Variations would require experimentation. The community's acceptance of Eli's system created a practical problem. Multiple families wanted to replicate the heating innovation, but the material costs remained prohibitively expensive for most settlers. Iron pipes were scarce and costly on the frontier. Thomas Brennan's fabrication time was limited. The blacksmith could not dedicate months to pipe production for multiple families while neglecting other essential metalwork the settlement required. James Caldwell organized a meeting specifically to address the economic constraints. He had been humbled by the temperature measurements and was now genuinely interested in implementing the system in his own cabin. But Caldwell was also practical. He calculated that purchasing materials and paying Thomas for fabrication would cost approximately $80 per cabin, equivalent to a full year's income for an average trapper. Few families had such resources available. The discussion revealed the settlement's economic diversity. 3 families had capital from Eastern inheritances or successful business ventures before moving west. They could afford the system immediately. 5 families were comfortable but could not justify such an expense without certainty of return. 4 families lived subsistence existences and could not afford the system under any circumstances, though they needed it most. Thomas Brennan proposed a solution drawn from his experience in Pennsylvania before coming west. Group purchasing. If multiple families committed simultaneously, he could order iron stock in bulk from St. Louis, reducing per-unit costs significantly. Instead of fabricating custom pipes for individual projects, he could standardize dimensions and produce multiple identical systems, dramatically reducing labor time through repetition and specialization. The economics were compelling. Individual purchase and fabrication cost approximately $80 per system. Group purchase with standardized production could reduce costs to approximately $45 per system. The savings came from bulk iron pricing, reduced transportation costs for consolidated shipping, and efficiency gains from repetitive fabrication. Caldwell did the broader calculation. If 6 families committed to installations, the combined purchase would justify a bulk iron order from St. Louis. Thomas could fabricate pipes during the winter months when other forge work was minimal. Installations could happen in spring and summer when weather permitted excavation. The timeline was aggressive but feasible. 3 families committed immediately. Samuel Hartwick, despite his advanced age and initial skepticism, committed second. He stated plainly that he had watched too many people suffer from cold floors. If engineering could solve the problem, he would invest in the solution. His endorsement carried weight. 2 additional families committed within days. Daniel Moss, the young settler who had observed Eli's sandbed installation, asked if he could work as Thomas's assistant during pipe fabrication. He offered labor in exchange for learning the metalworking techniques and receiving materials at cost for his own future cabin. Thomas agreed. The arrangement gave him needed help while training someone who could eventually provide metalworking services as the settlement expanded. By late January, 6 families had committed capital to the project. Thomas placed an order with a St. Louis metal merchant for iron stock sufficient to fabricate pipes for all 6 systems, plus Eli's original installation measurements as reference. The order would arrive by riverboat in spring. Installation would begin in May. The group purchase transformed Eli's singular achievement into a community-wide improvement in frontier living conditions. Spring 1849 brought the iron stock shipment from St. Louis. 240 pounds of quality iron arrived by wagon from the nearest river port, a journey of 3 weeks. Thomas Brennan examined the material carefully, checking for impurities or damage. The iron was excellent, better than stock typically available on the frontier. The bulk purchase had allowed the St. Louis merchant to select from premium inventory. Thomas set up a production schedule that would have impressed a factory foreman. He dedicated 2 full days per week to pipe fabrication, Tuesdays and Wednesdays, when his other forge commitments were typically lightest. Daniel Moss worked alongside him, learning to thread pipe ends using a die and handle system that Thomas had adapted from Pennsylvania metalworking traditions. The work was repetitive but required precision. By late April, the first complete pipe system was ready for installation. James Caldwell's cabin was selected as the initial replication project because Caldwell had volunteered his structure as a test case and because his cabin's dimensions were nearly identical to Eli's, allowing for direct technique transfer. Eli supervised the installation, working with Caldwell and 2 other settlers who wanted to learn the process before tackling their own projects. The excavation proceeded faster than Eli's original work. With multiple men digging and Eli's experience guiding the effort, they completed the floor removal and soil excavation in 8 days rather than 3 weeks. The efficiency came from understanding exactly how deep to dig, what soil could remain versus what needed removal, and how to organize the work to avoid redundant effort. Pipe installation revealed an unexpected challenge. Caldwell's cabin had settled slightly since construction, creating an uneven floor foundation. The settling meant Eli's precise slope calculations needed adjustment. He spent an afternoon with his water-level tool, mapping the actual floor elevation at multiple points, then recalculating pipe positions to maintain proper circulation despite the uneven foundation. The adjustment worked, but it taught an important lesson. Each cabin would require custom calculations even when using standardized pipe dimensions. The sandbed installation went smoothly because Eli had developed clear techniques during his original project. He showed the workers how to compact sand in layers, how to test compaction by pressing a wooden block into the surface, and how to avoid disturbing pipe positions while working around them. Daniel Moss took detailed notes, creating a written guide that would serve future installations. Samuel Hartwick visited during Caldwell's installation and watched the process with obvious interest. He asked technical questions about sand moisture content, pipe thread sealing compounds, and reservoir positioning. Eli answered thoroughly. Hartwick was not just curious. He was preparing mentally for his own cabin's modification. At 70 years old, he would not do the physical labor, but he wanted to understand every aspect of the system. By mid-June, Caldwell's system was operational. The first fire test produced circulation within 3 hours, faster than Eli's original system. The improvement came from refined technique and Thomas's increasingly precise pipe fabrication. Caldwell's family moved back into their cabin and experienced their first warm floor nights. The validation was personal and immediate. Joseph Klein arrived in the settlement in July 1849. He was a German immigrant with metalworking experience from Bavaria, where he had apprenticed with a coppersmith before political upheaval drove him to America. Klein was 41 years old, skilled, and looking for opportunities to establish himself in frontier communities where traditional European craftsmanship was rare and valuable. Thomas Brennan met Klein when the German visited his forge seeking work. Thomas did not need a partner, but he recognized Klein's skill immediately. The German understood metallurgy at a level beyond Thomas's practical knowledge. Klein could look at iron stock and assess carbon content by color and grain. He understood thermal expansion coefficients and how different metals responded to stress. His expertise was theoretical and practical simultaneously. Klein examined the pipe heating systems with professional interest. He praised the engineering, but identified potential improvements. Iron pipes worked adequately but were not optimal for heat transfer. Copper conducted heat approximately 5 times more efficiently than iron. A system using copper pipes would heat faster and transfer more thermal energy to the surrounding sand bed with the same amount of fire. The obvious problem was cost. Copper was significantly more expensive than iron, especially on the frontier where all metal had to be transported from eastern manufacturing centers. Klein acknowledged this constraint but proposed a hybrid approach. Use iron for the main circulation pipes where volume mattered more than conductivity. Use copper for branch pipes near the floor surface where heat transfer was critical. Thomas was skeptical, but intrigued. He and Klein worked through the economics together. A full copper system would cost approximately $120 in materials alone, more than double the iron system cost. But Klein's hybrid design, using iron for 80% of the pipe length and copper only for critical sections, would add only $15 to material costs while substantially improving heat transfer efficiency. Eli was consulted because his cabin served as the reference system. He listened to Klein's proposal and asked pointed questions about the junction points between iron and copper. Different metals expanded at different rates when heated. Would the connection points between iron and copper pipes fail under thermal stress? Klein had anticipated the question. He proposed using brass compression fittings that could accommodate differential expansion while maintaining watertight seals. The technical discussion attracted other settlers. Daniel Moss took extensive notes. Samuel Hartwick asked about long-term durability. James Caldwell questioned whether the added efficiency justified the added complexity. Klein responded to each concern methodically. The hybrid system would require more sophisticated installation but would heat living spaces approximately 30% faster and maintain warmth longer after fires diminished. 3 families who had not yet begun installation decided to attempt Klein's hybrid design. Thomas and Klein worked together fabricating the mixed metal systems. The partnership was mutually beneficial. Thomas had forge infrastructure and established community relationships. Klein had advanced metalworking knowledge and precision fabrication skills. Together they produced heating systems that represented the frontier's cutting edge of domestic engineering. The winter of 1849 to 1850 provided comprehensive validation of the underground pipe heating systems. 7 cabins in the settlement now operated with Eli's innovation in various configurations. 3 used pure iron systems identical to Eli's original design. 3 used Joseph Klein's hybrid iron-copper design. 1 used an experimental all-copper system that a wealthy settler had commissioned despite the cost. The performance differences were measurable but not dramatic. Pure iron systems maintained floor temperatures approximately 35 to 40 degrees above ambient outside temperatures when fires burned moderately. Klein's hybrid systems maintain temperatures 40 to 45 degrees above ambient with equivalent fire intensity. The all-copper system achieved 50-degree differentials, but at more than double the installation cost. All three approaches represented massive improvements over standard fireplace heating. More significantly, the health impacts became evident. The settlement experienced 0 frostbite cases during a winter that was comparably severe to the previous year when William Garrett had lost his toes. Children in heated floor cabins suffered fewer respiratory infections. The elderly reported less joint pain and better sleep quality. The medical benefits extended beyond simple comfort to genuine health improvements that families had not anticipated when committing to installations. Firewood consumption data surprised everyone. Intuition suggested that heating entire floors would require more fuel than heating rooms through standard fireplaces. The opposite proved true. Families with heated floors used approximately 30% less firewood than families with traditional heating. The efficiency came from the system's thermal mass effect. Sand beds stored heat and released it gradually, meaning fires could burn at moderate levels rather than requiring constant high-intensity burning to maintain comfort. Samuel Hartwick, whose cabin was among the hybrid designs installed that summer, kept meticulous records throughout the winter. He measured firewood consumption weekly, recorded interior temperatures daily at multiple locations, and documented subjective comfort assessments from his family. His data confirmed what others experienced anecdotally. The heated floor system was not just more comfortable, but more economical and more healthy than traditional heating. His detailed notebooks became reference documents that other settlers consulted when planning their own installations. By late winter, additional families were planning installations for the following summer. The initial group of 6 had expanded to 12 committed projects. The innovation was spreading not through advocacy, but through direct observation. Settlers visited heated cabins, felt the warm floors, saw the reduced firewood piles, and made practical decisions based on tangible evidence. Thomas Brennan and Joseph Klein formalized their partnership, establishing what amounted to the settlement's first specialized engineering firm. They took orders for pipe systems, standardized dimensions further to improve fabrication efficiency, and began training apprentices. What Eli had conceived as a solution to his personal problem had evolved into an economic enterprise that improved community welfare while creating skilled employment. By 1855, the heated floor technique had become standard in the Montana settlement and was spreading to neighboring territories. Traveling trappers and traders carried stories of warm cabins to other frontier communities. Henry Sutton, a circuit-riding minister who visited the settlement twice yearly, described the innovation in letters to Eastern missionary societies. Word spread through informal networks that connected isolated frontier populations. Eli Thornton was 51 years old. His daughter Rachel had married Daniel Moss, the young settler who had taken such careful notes during early installations. They were building their own cabin using the most current hybrid design. Eli supervised occasionally, but mostly stayed away. The technique no longer needed his direct involvement. Others understood the principles and could execute installations competently. The evolution of the technology continued beyond Eli's original vision. Settlers in different regions adapted the system to local conditions and available materials. In areas with clay deposits, some builders used ceramic pipes for portions of the system. In regions with access to soapstone, thermal mass floors used stone instead of sand. The core principle remained constant, but implementations diversified based on resources and ingenuity. Margaret Thornton maintained their original system with minimal maintenance. The pipes showed no signs of corrosion after 7 years of continuous use. The sand bed retained its thermal properties. The reservoir required only occasional refilling to replace water lost to minor evaporation. The system Eli had built in 1848 remained fully functional, proving that proper initial construction created infrastructure that lasted decades. Modern historical assessments estimate that Eli's innovation directly influenced construction techniques across the Rocky Mountain territories for the next 30 years. Cabins built with underground heating systems had survival advantages that translated to lower mortality rates in regions where winter cold routinely killed settlers. The exact number of lives saved is unknowable, but period accounts reference multiple instances of families surviving severe weather specifically because their cabin floors remained warm. The phrase, "built with Thornton heating," appeared in property descriptions and settlement records from the 1850s through the 1870s. The terminology indicated not just a technical feature, but a standard of construction quality that implied careful engineering and superior living conditions. Eli himself rarely discussed the achievement. When asked about the system by visitors or new settlers, he described the technical details factually, but without pride or self-promotion. To him, the warm floor was simply a problem solved through observation, calculation, and persistent work. The fact that others found the solution valuable was satisfying, but not remarkable. In 1871, Eli died quietly in his sleep. He was 67 years old. His grandchildren, including 3 born to Rachel and Daniel, had never known life in a cabin with cold floors. They played on warm surfaces, slept comfortably throughout winter, and took for granted conditions that would have seemed miraculous to frontier settlers just 25 years earlier. The impossible had become ordinary, which was perhaps the truest measure of successful innovation.